Hello students, welcome back to the Tantray physics classes. We are doing gravitation with the students. Today's question is variation of acceleration due to gravity due to rotation of Earth. As we all know, the Earth rotates about its own axis, which make day and night. It makes one complete revolution in 24 hours, and time period is 24 hours, and angular velocity must be 2 pi by t. How much angle it cuts in 1 second around its own axis, that is omega, that is 2 pi divided by time period of the Earth. So due to the rotation of the Earth, the effective acceleration due to gravity changes. In fact, it decreases because of rotation. But the effect on the equator is something, and effect on the pole is almost nothing, because on every Earth is like this, rotates. If you are on the equator, you are moving in a bigger circle with the Earth. If you are just above with some latitude, you are moving in a little circle. And in a little, if you are at the pole, you don't move in a circle. But when you are moving in a circle, you need a centripetal force to move in that circle. If you are outside the Earth, watching the object moving on Earth. But if you are on the Earth itself, then for you there is a centrifugal force, because then you are in a rotating frame of reference. So now it depends whether we want to solve the problem outside the Earth or on the Earth. So it is preferable to solve the problem on the Earth, because on the Earth the object is at rest with respect to us. So the net force on the object is zero for us on the surface of the Earth. Or you may say the acceleration of the object on the surface of the Earth for the observer himself is zero. It will be very simple for the observer who is on the Earth himself. But when you are on the Earth, there is one more force on the object in addition to real forces, that is centrifugal force. There's one more additional force for you on the surface of the Earth, on the object, that is centrifugal force. But if you are outside the Earth and watching the object moving in a circle, there is a centripetal force on the object which moves in a circle towards the axis of the Earth. But now let us solve the problem for the observer on the Earth himself. So this is the object here, somewhere at latitude lambda. It moves in a circle of radius small r. Of course, there is a relation between r and r, or it is small r is in which the object moves in a circle there because of the rotation of the Earth. It is r cos alpha, r cos lambda, equation number first. And when it moves in a circle, for the observer on the Earth, there is a centrifugal force, mr omega square, where omega is the angular velocity of the Earth about its own axis. And this is a normal reaction n. And towards the center of the Earth, there is gravitational force. So how many forces are there on this object? 1, 2, and 3 forces. For a person on the surface of the Earth. Because the person on the surface of the Earth is in the non-inertial frame of reference. For him, there is an additional force, that is centrifugal force, which acts away from the axis of the Earth because of the rotation of the Earth. Okay, what is the component of this force in this direction? That is plus mr omega square cos of lambda. Mr omega square cos of lambda. So the net force on this object for this person is zero. Therefore, this force is balanced by the gravitational force. So gravitational force is G capital M small m, that is the force on the object, divided by r square, is equal to force in the normal direction, that is n plus mr omega square cos of lambda. What is normal reaction now? The normal reaction can be written as G capital M small m by r square minus mr omega square cos of lambda. Now n normal reaction is weight. The normal reaction on the object by the surface of the Earth is weight. That is the apparent weight. This is mass into acceleration due to gravity at this effective acceleration due to gravity there at that position, at that latitude. So that is g capital M small m by r square minus m r omega square cos lambda. M gets cancelled throughout. So what is g lambda? That is gm by r square minus r omega square cos of lambda. Now, what is g lambda? What is g lambda? What is g lambda? Acceleration due to gravity here at this point at latitude lambda. Because of the rotation of the earth, it will not be the same as gm by r square. What is it? It is gm by r square. That is okay. Let me write it g. Acceleration due to gravity, had there been no rotation. Without rotation, this would have been the acceleration due to gravity. But with rotation, it is g minus r को substitute कीजिए r cos lambda, that is r omega square, this one cos square lambda, because it is when we substitute r is equal to r cos lambda. Equation number second. This is the effective acceleration due to gravity here. G, had there been no rotation, had omega been 0, then g lambda would be g, 9.8. But acceleration due to gravity is not g, but is g minus something, that is r omega square cos square lambda. This negative quantity, this quantity is due to rotation of the earth. So this is the actual acceleration due to gravity with rotation of the earth, g minus r omega square cos square lambda. Okay. Now, what is the acceleration due to gravity on the equator? Acceleration due to gravity at equator. That is acceleration due to gravity at equator. That is g minus r omega square cos square 0, because lambda is 0 on the equator. If the object is here, lambda is 0. So it is g minus r omega square. This is the acceleration due to gravity at the equator. So there's a lot of effect at equator due to the rotation, minus r omega square. What's the acceleration due to gravity at equator? Equator. What is the acceleration due to gravity at poles? Poles here or here. But you know, if the object is here, it moves in a bigger circle of radius r. If it is here, it means little circle. But if this object is at the pole, it will spin because of the Earth's rotation, but it no longer moves in a circle. So at the poles, the effect will be least. There will be no effect at all. So what is the acceleration due to gravity at the poles? Acceleration due to gravity at poles. Acceleration due to gravity at pole. Acceleration due to gravity at pole. That is g minus r omega square cos square lambda. But lambda here is 90. If you are here, lambda will become 90. Here it is 0, it is 90. So gp is equal to g minus r omega square cos square 90. That is gp is equal to g minus r omega. Sorry, cos square lambda is 0. So no effect. So there is no effect on the acceleration due to gravity at the pole, because rotation will have no effect, because this on the top, the object no longer moves in a circle. It spins there at the top, but it does not move in a circle. Okay. So now the example, I made an example like this. What should be the angular velocity of the earth about its axis so that object flies off from the surface of the earth? It is earth, it rotates, and objects on the surface of the earth, as we all know, stick to the ground because of gravitational force, because of gravity. But if the earth's rotation may have been higher, if earth rotates faster, omega is more and more, there is a possibility that the object on the earth may fly into the space, or it may be thrown off into the space. ये space में चला जाएगा, object को earth repel करेगा into the space. Why is that? Because if omega increases, then r omega square factor जो हमने अभी लिया है, r omega square factor will also increase. So a time will come when the effective acceleration due to gravity on the surface of the earth will be 0 because of the higher rotation of the earth. So at that time, the objects can fly off into the space. You start floating on the surface of the earth. Something like this. If omega, what should be omega so that this object is thrown into the space at the equator? The problem is for the objects on the equator. And the answer will be different at different places, but we will find the answer for the equator. For equator position. For equator position. What should be this omega of the earth so that the object is thrown into the space? Or it flies off into the space. The answer is like this: G equator is equal to G minus R omega square, which we got right now. When the object is thrown into the space, that means there is no acceleration towards this center of the earth. That means its weight is 0. That means its acceleration toward the effective acceleration toward the center is 0. When its acceleration toward the center is 0, when its acceleration is 0 towards the center, that means this is 0. So it's G or omega square. So that will give omega square is equal to G by R. So that will give omega is equal to root of G by R. Answer. You can substitute G. You can substitute G and R, you can get the answer. We can also find the time period, which is 24 hours right now. We know the time period of the earth about its own axis is 24 hours by our major standards. So omega is equal to root of G by R. It is 2 pi by T is equal to root of G by R. T is equal to 2 pi root of R by G. This is the time period. T equal to 2 pi root of R by G. If you substitute the values, you will get T is equal to 86 minutes approximately. That means if the time period of the earth about its own axis is not 24 hours, it is only 86 minutes, so it moves very faster. Jo earth par objects honge, they will start floating, they will start moving away from the earth, moving above the earth into the space. Right? Second example that I have framed is, what is the change in weight of an object when it moves from equator to 60 degree latitude? एक ऑब्जेक्ट को यहाँ से यहाँ लिया जाता है 60 डिग्री लैटिट्यूड पर, तो वेट में कितना फर्क आएगा? इसमें बहुत ही कम फर्क आएगा. After all, omega is very small. Omega is 2 pi by T. Is 2 divided by 24 hours. 24 hours को अगर हम seconds में convert करेंगे denominator में, तो omega का value बहुत ही कम होता है. So the change is not much, but there is a small change. So what is weight here at the equator? W1, weight at equator. Weight at equator. कितना है? That is, okay, mge, mass into acceleration due to gravity at the equator. That is m times g minus r omega square. वजह यह है कि ge जो है, that is g minus r omega square at the equator. So it is W1 is equal to mg minus mr omega square. This is weight at the equator. Now let me find weight here at 60 degree latitude. What is the weight there at the 60 degree latitude? Okay, again write down the formula, same formula there, and let me see. तो formula क्या है? तो उस पर जो 60 degree latitude पर g क्या है? That is g minus r omega square cos square lambda. That is m को multiply करने से throughout, multiply m throughout. This becomes weight there, W2, weight here. It becomes mg minus mr omega square cos square 60. The W2 equals mg minus mr omega square cos square lambda is cos 60 is 1 by 2 as 1 by 4. Okay, because cos square 60 is 1 by 4. तो ये हुआ W2. W1 you know. So what is the change in weight? Delta W is equal to W2 minus W1. Weight here will be more because G here will be greater, and G here at the poles, pole top, these positions will be highest, will be greatest, because there is no effect on rotation. There is no effect of rotation. So W2 is mg minus mr omega square by 4 minus W1, that is mg, minus into minus means plus mr omega square. This cancels off, so this is equal to, इसको subtract करने से it is 4, it is 3m omega square, 3m omega square by 4. This is the answer. M r omega square minus m r omega square by 4, that will make it is 4, that is 3m r omega square by 4. So this is the change in weight. When you go from equator position to 60-degree latitude, your weight will be different, but the weight will be different. Of course, the weight will increase, but slightly, because here is m r omega square. R कितना भी ज्यादा क्यों न हो, m कितना भी ज्यादा क्यों न हो, लेकिन ओमेगा स्क्वायर से ये जब मल्टीप्लाई होगा तो इट विल रिड्यूस ऑलमोस्ट टू नेग्लिजिबल क्वांटिटी. ओमेगा स्क्वायर, यू सी ओमेगा इज 2 पाई बाई टी, और उसको स्क्वायर करो तो और भी रिड्यूस हो जाता है इसका न्यूमेरिकल वैल्यू. So this was fourth lecture on gravitation. The series will continue, but don't forget to download the app, Tantray Sir Physics classes, and also continue to watch my lectures on YouTube. Thank you.